the key thing of looking at the examples that we did, they were not very computational, but they were really just trying to dig into what this means at the top here. So again, just stated, again, because it is just so important, how is an equation in x and y related to its graph? So you've got two things, right? There's that equation. Right? Let's just go back to to like right here. There's an equation right here, and that equation has many points on it. And how does this picture in this circle, that shape, relate to the fact that there's this equation here at all, and which points are on it and which points are not, right? So this like green point is on it and this blue point wasn't. How did that happen? And that's what this is about. It's that you have a point being part of the graph if that point satisfies the equation, and a point is not part of the graph if the point doesn't satisfy the equation. Please carefully process the words that are mentioned here. It's important to really process these words. It's not just a matter of memorization. Actually understand what this is saying. Connect it to the examples we just did. The thing is, sometimes people will try to say words like the following as an answer to the question, how's the equation related to the graph? These following things don't actually make any sense. So I've seen people say things like the equation is related to the graph if the equation is satisfied, and the equation is not related to the graph if the equation is not satisfied. And hang on, the equation is always related to its graph. You have an equation in x and y, it's always related to the graph. It's just a question of how. It's a question of which points are part of the graph. The first sentence is trying to explain which points in the plane are part of the graph. So to be in the club, so to speak, a point needs to satisfy the equation. And the second sentence is trying to explain which points are not in the club, right? So if a point is not part of the graph, if the point doesn't satisfy the equation. Okay, so there it is again. An equation in x and y, again, just to try to clarify, is it always has a graph, and that graph is always related to the equation. The text here in the blue box is trying to help us understand what that connection really is. So you don't want to say something like the equation is unrelated to its graph. No, it's always related to its graph. We're just trying to now talk about the individual pieces of the graph, which are the individual pieces are points. We're just trying to ask, how do we know what points belong to the graph and how do we know which ones don't? It's just a matter of trying to draw in all of the times that the equation is satisfied. Again, going back to say the last example here, or maybe the example before, the whole point is to say all of these points along here, like this point right here. I mean, I know it's messier, but let's take this point here, 0.71 comma 3.364. That point satisfies this equation. That's all we're trying to say, is that every single point here satisfies the equation. And then what about a point like over here? What is this? 7 comma 3. Well, that point just doesn't satisfy the equation, so that's why it's not part of the graph. Okay, the graph is really supposed to be then a visual summary or representation of the equation, but this can only be useful if we understand that the picture really shows all the points that satisfy the equation and shows none of the points that don't satisfy the equation. So it shows the points that doesn't show the points that doesn't, right? The graph is truly every point shown here in black is an example of a point that satisfies the equation, and every point that wasn't shaded in black is just an example of a point that doesn't satisfy this equation here.